Hello there, this is lecture 4 on section 2.3, trig limits and squeeze theorem. So we're going to move on. So far we've looked at limits as we approach polynomials and rational functions at a point and to and from infinity. But we haven't looked at any of our special functions, so let's take a peek at how some of our special functions are going to work. So we've got four functions, e to the x, ln x, sine x, and cosine x. So let's take a quick second and let's go ahead and graph these functions. So I'm going to start with y equals e to the x. And e to the x looks like this. It crosses at 1 and looks something like that. Now ln is its inverse. So for ln, we're going to flip this around the line y equals x. So now you get this point on your graph, and it looks like this one. So that's your y equals ln x. Now for your trig functions, we're going to set this to be 1, and 1, 2, 3, 4, this to be negative 1. And for sine x, we start at 0, and it's going to become a oscillating function back and forth between negative 1 and 1. The difference then for cosine is you get the same shape between 1 and negative 1, only this time you're going to start at the top. So you're starting up here at 1, and you're going to oscillate back and forth from there. So if we then use these 4 graphs to fill in our limits, so we've got e to the x here on the left, and we want 0, infinity, and negative infinity. So with 0, we would plug in our 0, and e to the 0 is just going to be 1. As I mentioned, we get the 0.01, so that's the limit. Now, as you're going to infinity, if you look at the graph and we trace it, you're heading up. So that's going to tell us that as you go to positive infinity, e to the x goes to infinity. And then as you head towards negative infinity, what happens is if we follow our graph, it's going to hover right here as an asymptote along 0. So it's going to get closer and closer to 0, even though it's not going to get there. So our limit is going to be 0. For ln x, notice that as ln of x goes to 0, we only look at it from the right, and that's because our graph doesn't exist on the left. So if we're going to talk about a proper limit here, we can only approach from the right. And you can see that as we go to 0 from the right, we're headed down. So the limit there is going to be negative infinity. As you go towards positive infinity and you follow your graph, this arrow is headed upward over time. So we're going to get positive infinity on that one. And then, of course, the graph doesn't exist on the left-hand side. So as we go to a negative infinity, this just doesn't exist because there's no graph over there. For, let's start down here at the bottom. I'm going to go to cosine of 0. So when you plug in 0, cosine of 0 is going to be 1, right? At 1, we started at the top of the curve right here. Right? So that's our value there. Now for sine and cosine, as x goes to infinity, let's think about these graphs for a second. So as we head to the right on both of these graphs, it's going to oscillate back and forth the same way for both of those. And so we're just going to bounce around. And what that means is that I'm not approaching a specific number. Because if you pick 1, I can choose a larger number that moves away from that. And if I choose negative 1, I can choose a larger number for x that moves my value away from negative 1. So what happens here is that our limit just doesn't exist. There is no number that we approach. Okay? So these two are both does not exist. Okay. So at a value, our trig functions are fine, but at infinities for sine and cosine, we get something that does not exist. So does that mean we never have limits if cosine's in our function? Not necessarily, okay? So suppose that we want to graph the position of a bungee jumper over time. What would that graph look like? Well, let's suppose that this is our equilibrium at x, at our x-axis. So our bungee jumper is going to stay way up here. And our bungee jumper is going to dive off the ledge, and it's going to go past equilibrium down here, and the bungee is going to make them turn around. And you're going to come back up. But you don't come up as high as you started. And our bungee jumper's range of motion is going to slow down over time. And eventually, if we let him sit there long enough, he should stop at an equilibrium position. Now, this graph, as you go to infinity, does in fact approach a limit, right? This graph is approaching 0. So a function that's going to match this behavior is this one, e to the minus t times cosine of 10t. What does the 10 do here? The 10 just kind of squishes or extends my the oscillations. The e to the negative t is what's going to take it down to 0. And the cosine is what causes the oscillations. And of course, our jumper is jumping at time t equals 0, so we're going to have our restricted t greater than or equal to 0. So again, if we looked up here at this graph and we follow our function as we head out to infinity, these numbers are approaching 0 from both sides. So when we look at the graph to determine the limit, this is going to be 0. Okay, so the question is, how can we do this without the graph? Well, we have a theorem that's going to help, and this is called the squeeze theorem or the sandwich theorem. And that tells us that if we have 3 functions, a small one, a big one, and one in the middle, on an open interval that contains a c value, right? So you've got to be on some interval, some space, where you have the x value that you're going to take the limit of, okay? So what happens is, if the limit of f and the limit of h, so the small one and the big one, over time are going to go to the same value, they're going to approach the same number, then the one that's between them has to go there as well. Okay, it's going to sandwich the g of x function between the larger function and the smaller function, and it's going to send it to that same value. Okay, essentially, it looks something like this. So if this is my g of x that I'm trying to say has a limit 0, what I want to do is I want to find a function up here that is larger than the green one at all times, but that approaches 0. And I want to find one below that approaches 0 from both sides. And so if the red and the blue graph are approaching 0 from both sides and my green one has to stay between them, then there's nowhere for the green one to go except to that particular value. Okay, and so that's how our squeeze theorem works. And it works best with trig functions that have oscillations just like this. So how do we show this? Well, the first thing we want to do is we want to build that inequality. So we want our function in the middle with 2 functions on either side. And the way that we build that is we start from the trig function. So here is my trig function. So I'm going to start with the cosine of 10t. And I know that the cosine of anything is going to stay between 2 values. It's going to stay between -1 and 1, just like on our graph. Then I want this function right here in the middle. I want that to show up here. Well, I don't have it yet, so I need to get in that e to the negative t, and that e to the negative t is multiplying my cosine. So I'm going to take all 3 pieces of this inequality, and I'm going to multiply it by e to the minus t. If I do that and I distribute to all 3 parts of my inequality, that's negative e to the minus t, less than or equal to e to the minus t cosine 10t, less than or equal to e to the minus t. And now you can see that this green function up here now sits in the middle. Okay, so I have satisfied the first criteria for the squeeze theorem. I have my function g of x fitted between 2 other functions, one smaller, one larger at any time. Okay, so now what I need to show is that the limits of the outer 2 functions go to the same value. So that's what I'm going to do next is I'm going to take the limit of all of these things. So that's the limit as t goes to infinity of negative e to the negative infinity is less than or equal to the limit as t goes to infinity of e to the minus t cosine 10t less than or equal to the limit as t goes to infinity of e to the minus t. So I can take the limit of all 3 pieces. And what I want to show is that the 2 outer ones have the same value. So if we go up here and we plug in and evaluate our limits, on the left I get negative e to the negative infinity. I have my function in the middle. And on the right, if I plug in my infinity, that's e to the negative infinity. Okay, so I have negative e to the negative infinity and positive e to the negative infinity. If I go back up to my graph, e to the negative infinity is the same as e to the x as x goes to negative infinity, because that's what I plugged in. So if I'm on my graph and I'm headed towards negative infinity, the exponential function is headed to 0. So my values for e to the negative infinity are going to be 0. So that means that on the left here, I have negative 0, and negative 0 is just 0. I keep my limit in the middle. And the one over here, e to the negative infinity, is 0. We just showed that. So take a look what happens. My limit then has to be bigger than or equal to 0 and smaller than or equal to 0. So the only option by squeeze theorem is that my limit, the limit as t goes to infinity, of e to the negative t cosine 10t has to be equal to 0. Because it's pinned between two zeros. Okay? So that's what we want to do. Or anytime we see a limit to infinity that involves a sine or a cosine, we're going to pick out that trig function. Sorry. We're going to pick out that trig function. We're going to bound it between the two appropriate values. -1 and 1 often work. We're going to do some algebra to build the function we're trying to find the limit of. So we get that in the middle. Once we do, we can take the limit of all three sides and evaluate it. And we should get the same two values on the outside so that we end up with our limit in the middle by squeeze theorem is the same value. Okay. I am going to record these three in a separate video.